We're going to introduce ourselves. My name is Jonah. I am a student at Worcester Polytechnic Institute studying computer science. I'm an alum of Team 6328, and I'm currently a software mentor as well as a WPILib developer.
My name is Neil. This is my third year on the team. I'm a software student, and my favorite color is blue.
My name is Mantha, and I'm a senior, and I'm the software lead.
Thank you. And also, as you may have noticed, my voice is not great today, so I do appreciate your patience if I have to take a pause from time to time. Okay, so here's what we're going to be talking about today. We'll start off by looking at levels of logging in FRC. We'll talk about how to get started with logging. We'll then go through what AdvantageScope is and a couple of case studies exploring it. We'll talk about merging data sources and a couple of additional case studies. And then we'll end with a section on advanced visualization with one case study as well as an exclusive sneak peek of an upcoming AdvantageScope feature. So that should be pretty fun.
Cool. So first, before we get started, it's important to break down what data logging can actually mean in FRC. So we decided to break this down into 3 levels. The first would be driver station logging, second being onboard logging, and the third is log replay. So let's talk about each one in a bit more detail. So level 1 is driver station logging. And this is easy to set up. It's actually built into the FRC driver station. This is all automatic. And you can record simple data such as your battery voltage, your current draw, your network diagnostics, console text, anything you decide to print out. And this is easy to use and good for simple issues in field diagnostics, but it's not very customizable. So you may find that some fields that you want when you're analyzing your logs you don't have. So our second level would be onboard logging, and this is recording data to a USB drive on the actual robot. You may even use network streaming for live visualization to get live info from the data, or from the robot. And there are a few options for this. You may use WPILib for robot code logging, so you might log the stuff that's actually going through your logic. You may use CTRE signal logging, or you may use level logging, which is unofficial, but it's still usable. We use this for AdvantageScope. And level 2 logging in general is much more customizable than our level 1 driver station logging because you can use fields, or you can customize the fields that you want to log. However, if you forget to log a single field, that's unretrievable. So that brings us to level 3. Level 3 is a bit more advanced than all the other ones. This is our more advanced form of logging. And so we won't be talking about that in this session. Feel free to stick to the next session if you want to hear more about this.
Okay, so now that we've discussed what logging can look like in FRC, let's dive into some specifics. So if you're just using driver station logging right now, which is level 1, I cannot recommend highly enough that you at least explore level 2 logging a little bit. And remember that level 2 can include both network streaming as well as log files. Now, there are numerous options now for onboard logging in FRC, and all of these require just a few lines of code to get started, so it's super easy. We'll have links to more information about all of these options at the end of the presentation. Okay, so the first set of options are built into WPILib. It now includes several options for doing data logging. This might include data like joystick inputs, your odometry pose, subsystem state, PID errors, anything you can think of from the robot code itself. Now, network tables is WPILib's standard protocol for publishing data to the network, and the data log manager class can capture all of that network table's traffic to a log file. This is by far the easiest way to get started with robot code logging. And you can see on the right we have some example Java code of what that looks like. There's just 2 lines in robot init to start the data log manager and capture driver station data, so that's your robot state, joysticks, etc. You can then publish any data that you want to network tables. There are multiple methods. We've shown a simple option using the Smart Dashboard API. And optionally, you can use a third-party library called Monolog, so you can annotate methods and fields to be logged periodically without any additional work. Now, this year, there are also several options for logging data directly from vendor devices. For 2024, CTRE introduced their Signal Logger for Phoenix, which captures data from some of their devices to a log file on the Rio. Those devices include the Talon FX, Pigeon 2, and CanCoder. The Signal Logger is super easy to set up. You can see what that looks like here in Java. And in fact, even if you don't add these lines, the Signal Logger is automatically started whenever you're connected to the FMS. Though I do want to note that in C-Theory's case, the set of available signals is extremely limited for logs that don't include at least one Phoenix Pro licensed device, so keep that in mind. Now, C-Theory does also include a diagnostic server on the Rio. There's no setup required for that, and that allows signals from all of their devices to be plotted over the network. Okay, now while Rev does not include an official logging option for their devices, we've developed an unofficial alternative. We call it URCL, or the unofficial Rev-compatible logger. Again, it's just a couple of lines of code to set up, and then it will automatically capture data from all Spark Max and Spark Flex devices on the CAN bus, similar to C-Theory's signal locker. All of that data is sent to network tables so it can be viewed live over the network, and it can also be captured using the data log manager to a log file, just like any manually published data. So here we have an example of how all of those systems can be used together. Up at the top in Robot Init, we have some general logging set up where we start the data log manager and driver station log. We also enable URCL. In this example, we're using Rev hardware, but you could use the C-Theory signal logger instead. That'll automatically capture lower level data from our devices. Speaking of which, we have some hardware set up for the Spark Max in our flywheel. And then here we have some code that's using traditional WPILib logging, sending data to network tables using the Smart Dashboard API. All of this will be captured by Data Log Manager and available after the fact. Now there are several data types that are supported here, so you could log Booleans, strings, numbers, arrays, lots of types. We also have a section here, though, showing how to use Monolog. This allows you to log data using annotations. And Monolog has really great support for complex types, like geometry objects, translations and poses and rotations and whatnot, so you can store those directly. Now, WPILib supports that too, but Monolog provides a really nice, easy-to-use API for that. Now, you can also see that fields and methods can be annotated, so that those are logged periodically, so there's no need for an explicit logging call. At the end, we also have an example here of non-periodic logging. So here we're logging the set point for our flywheel in line. Now, many fields we do want to log periodically, but that's not the case for everything. We aren't always setting a set point, for example. Now, another example where this might be useful is if you have a subsystem with multiple states, you could log that state only when it changes. So both periodic and non-periodic logging can have important use cases.
So how do we visualize all this data? There are several options, but today we're going to be talking about AdvantageScope. This was developed by 6328 starting in 2021 and is now included in the 2024 WPILib installer. So what is AdvantageScope? Well, it's a programmer's tool for data visualization, and it supports all the levels of logging that we talked about previously. It supports network streaming and log viewing in one application and hosts a variety of visualization tools. Here's a complete list of the visualization tools available in AdvantageScope. You can see we have basic views like line graphs and tables, and then some more complex views like 3D fields, joystick views, and swerve diagrams. Many of these views can even be combined. Because AdvantageScope is already included in the WPILib installer, you probably already have it installed on your laptop. To get started with AdvantageScope in VS Code, you can simply click the three dots on the top right corner, go to Start Tool, and then choose AdvantageScope. Additionally, you can also download it from GitHub, where we support additional platforms and where we also include more example robot models. AdvantageScope also has extensive documentation available within the app. To access this, simply click the book icon in the app. Here you'll see how to interact with different data sources, how to use each visualization, and how to import custom assets, basically how to use AdvantageScope.
So this brings us to our first case study, which is arm tuning. So for this case study, we'll be going over our 2023 robot named Banana Split. And this is a swerve robot that has a triple jointed arm, which consists of the shoulder, the elbow, and the wrist. And for each one of them, each joint, we have to tune the PID and the feed forward model. So we can go over how we're going to use AdvantageScope to do this. So first, let's go over how we might analyze the arm behavior through AdvantageScope. So first, we'll pull a log from one of our previous events. Here, we're going to, in this example, we're going to pull out the measured and the set point angles for the elbow. We can zoom into the match to find the more relevant data. right here. And we've also included when the robot is enabled in the discrete fields. So here the units are radians. We might want a more familiar unit such as degrees because it's easier to analyze logs and stuff that we can interpret. So we can see here in this graph, we can see that the angle tracks pretty well, but maybe we want more of a visual representation of what's actually happening on the robot. So we can utilize the mechanism 2D object that WPILib provides us with. You may be familiar with it, and we can log the mechanism 2D from the data file. So here we're going to create a new tab. We're going to go to the mechanism, and we're going to see our visual representation of our arm. So keep in mind, this is replaying the match in real time, and we can see a 2D representation of the 3 joints on our arm. This is fine, but it's still a little bit abstract, so we can go to our final visualization, which is our 3D field. AdvantageScope allows us to import the robot CAD for visualization, and here, as we go on, we can see by combining the odometry of the robot data along with the arm encoders on the arm or the wheel encoders, we can see a whole complete representation of what the robot's doing on the field in live time. AdvantageScope can also connect to the robot using network tables, which allows us to connect to the robot and its data live. So this may be useful, for example, when you're doing driver practice and you want to see what's happening on the robot in live time. Another useful view that we can use is the statistics view. AdvantageScope can automatically create a histogram like this, and it can automatically calculate multiple statistics like the absolute error based on a measurement between the set point and the actual measured encoder value. So here we can see that AdvantageScope automatically created our average error for the elbow across a whole match. We can see our mean was 0.025 radians, or around 1.4 degrees, which is pretty good. You can also see other statistics such as the percentile. Here we can see our 99th percentile is 0.121 radians, which means that 99% of our error is under 7 degrees, which is pretty good. But let's say we still weren't satisfied with the performance that our arm had, and we want to retune the controllers. Well, the good thing that AdvantageScope allows us to do is we can tune this in live time. So the robot project allows us to accept PID gains over network tables, so we can connect to the robot and easily adjust gains on the fly. Here we can click the sliders button to enter tuning mode. We're running an auto routine right now to show the multiple instances of the arm. And as we plot the wrist measured and set point position, we can change the KP gain and the max acceleration, and the robot can respond in live time. We can also use techniques like this to tweak the code live during driver practice. For example, in 2022, for Rapid React, we might have wanted to tune the flywheel speed for shooting the balls into the goal. So this is a great way to see the effects of tuning under realistic match conditions.
Next, let's take a look at vision processing. This is an area where good logging is especially critical for diagnosing issues. For context, we developed a custom April tag tracking software called Northstar. The goals to this are similar to Limelight or Photon Vision, where we want to estimate the robot pose based on visible tags. Our 2023 and 2024 robots use this with 4 cameras. Today, we'll stick with an example from 2023. So here we've opened up the 3D field view tab, and so we can look at the field from a bird's eye view. We'll drag out the fields for individual robot pose estimates and the list of visible tags here. As we play the log, you'll see these green lines. These represent the tags that the robot detects. The translucent green ghosts of the robot show each individual pose estimate. A cool thing about this is that we can actually run this faster than real time. So we right-click there, go to 400% speed. This is really useful. If something went wrong during the middle of a match, we can quickly skim through the entire match using this to track down the problem very quickly. Again, all this data can be viewed live over the network when connected to a robot. And we don't need to stick to a bird's eye view either. We can recreate the video from each of the 4 cameras based on the robot's position. This allows us to see the tags this allows us to see when the tags should be in view of each camera, and we can even see when mechanisms might be blocking other tags. Another way to view this visualization data or localization data is by creating a heat map of the robot's movements throughout the match. This is useful for both analyzing the localization accuracy and to do match review with drivers.
Okay, so those were both examples of how we can analyze log data using AdvantageScope. But that's not the only tool that's available to us. So we're going to go in a slightly different direction now. Now, system identification is a powerful tool that's built into WPILib, and this year it depends on log data. So in general, system identification is the process of determining a mathematical model for the behavior of a system through statistical analysis of its inputs and outputs. Typically, inputs would be things like voltage, and outputs might be position and velocity. So we're trying to relate those two mathematically. Now, a really common example in FRC is that we might have a desired velocity and acceleration, and we want to calculate what voltage we should apply to a mechanism in order to achieve those set points. This is called a feed-forward model. It's useful in lots of different mechanisms like drives, flywheels, arms, etc. Now, we said this is a mathematical model. Here's a simple example of what that can look like. So here we're converting velocity and acceleration into voltage. And you can notice that there are three gains here, Ks, Kv, and Ka. Ks is constant. That only depends on the direction of the velocity, and that accounts for static friction in the mechanism. Kv is converting velocity to voltage, so the higher the velocity, the higher the voltage, and Ka works similarly for acceleration. Now, the WPILib docs go much more in depth into why this works if you're curious about the underlying math, and they also show how this can be extended to work for more complex mechanisms that have external influences. What we're going to focus on right now is how we can determine those gains. Now, they can be modeled theoretically if you have the CAD of your mechanism, but this often doesn't perform well in practice. The reason for that is that friction in a physical system can be very unpredictable and hard to model. So instead, we can measure those gains using log data. Now, WPILib has some built-in tools to run system identification. It needs to gather data over a series of 4 routines, which we need to set up in code. This would typically go in your subsystem class. You can see here we're defining a setter for voltage and getters for voltage, position, and velocity. We then have 4 tests, which are defined as commands, and we can run those during autonomous. There are 2 quasi-static tests and 2 dynamic tests, which you'll see in a moment. Now, rather than logging data through this, you also have the option of logging data directly using the vendor logging options we talked about earlier. You'll want to consult the relevant documentation for exactly how to set that up with sysid. Okay, so now we're going to run our 4 tests in auto. Here's a simple example with a differential drive. So first we're doing our quasi-static tests. This is where the voltage slowly ramps up, and we're looking at how that affects the velocity as it increases. So the relationship between voltage and velocity. In a moment, we're going to run it in reverse as well. So the reason we run these both forward and backwards is to make sure that we don't have any funny differences in friction going the 2 directions. Now we're going to run the dynamic forward and reverse tests where we step up the voltage quickly, and we're measuring how the robot accelerates. So this will give us a value for Ka. And this whole time, we're recording data from the sensors on the mechanism. This is also applicable to other mechanisms. So whether it's a swerve drive or flywheels or arms, all of them use these same 4 routines. So using all of that log data that we recorded during the tests, we can start to analyze it. And first, we might want to browse it in AdvantageScope. So here you can see along the bottom is our test state, and then we're showing the position of a swerve module over time during the test. It slowly ramps up during the 2 quasi-static tests, and you can see it accelerates much more quickly during the latter dynamic tests. And the final step is to actually calculate those gains. So here, using WPILib's system identification analyzer, we'll open up the log file. Then we need to drag out our test state, as well as the voltage, position, and velocity. This is so the tool knows which fields to analyze. We're then going to select the mechanism type as simple and set our units to radians, and then we tell it to load. So it ran the analysis, and right here you can see those calculated feed-forward gains, Ks, Kv, Ka. Now you may notice there's also a lot of other stuff we could dig into here. There are graphs. It'll even try and figure out the optimal feedback gains for PID controllers, but one of the most common use cases is just to see these 3 feed-forward values. And now, let's say we applied those new gains to our swerve drive, we can check the performance of it in AdvantageScope. And when tuning a swerve drive in particular, there's this built-in visualization that can be helpful for that, showing the vectors of how each wheel is moving. So here, these are in red are the measured positions and velocities, and in blue are the set point states. So we can see that it seems to be tracking the set point fairly well. On the left, you can see more specifically on one of the modules how the set point and the measured velocity are matching up during an auto routine. So it seems like this is performing very well, and we didn't have to manually tune any of our feed-forward gains to make this happen. So the system identification was a success.
So now let's talk about merging data sources. There are lots of potential data sources we're interested in, such as log files of different formats. This includes WPI logs, driver station logs, and CTRE hoot logs. There are also external data sources that we're interested in, such as match video and Zebra MotionWorks data. All these sources need to be loaded and synchronized. AdvantageScope can automatically merge all this data automatically merge all these formats. There's no need to manually sync up log files or switch between different viewers.
Yeah, so here we have a simple example of data merging. This is sort of a follow-up to our April tag case study. Now, you may already be familiar with Zebra MotionWorks, which is available at some events to track the position of robots on the field. It works using 2 tags mounted to each robot. You can see an example on the right, as well as sensors that are spaced around the field. The data from Zebra MotionWorks is published to the Blue Alliance, and often it's really useful for analyzing overall match play, but we can also use it to verify the accuracy of our robot's onboard localization. AdvantageScope can actually download all of this data and merge it in automatically. So here we're just going to click one button in the menu bar for Load Zebra MotionWorks. AdvantageScope will find this match on the Blue Alliance, download the data, and sync it up with our local log file. So now as we watch through the match, we can compare the Zebra data and the onboard localization. So here the translucent green robot represents the Zebra pose, and the solid robot represents our onboard pose. Now let's go a little bit more specific here. So now we're looking at the x-coordinates from Zebra and the onboard localization compared on the left. Now the tracking here is pretty good, but we want to pay attention to the areas where we have error. So one place is whenever we're at the end of the fields here. This is when we're right next to the nodes. But in this case, the error actually seems to be mostly with the Zebra data. So here's a comparison. You can see again the translucent robot is where Zebra says we are, and the solid robot is where the robot says it is. And in this case, I'd be more inclined in this case, I'd be much more inclined to trust the robot's localization. Now another place where we see some issues is right here. And this is actually where we collide with another robot in the middle of the field. Here's what that looked like during the match. So you can see we collide at full speed with citrus circuits, and so our wheels continue turning. The robot thinks it's moving, but it's actually come to a stop. So this is a case where the robot's onboard localization was worse than the Zebra, but we were able to see that using this source of reference. But overall here, you can see for most of the cycles, it seems to be tracking quite accurately. So this is a good confirmation that our onboard localization is doing what it's supposed to.
Another data source you might want to merge is actual match videos. So whenever things goes wrong, it's usually important to distinguish between where the error occurred. Was it in the driver, how he was driving the actual robot, or was it actually in the software? Did we make a problem that we didn't identify? Being able to merge the actual match video and compare it to the log files is important because we can solve the issue pretty efficiently. We can see it in real time and how it might be represented in the data. So here we have a log file, and we want to see what the robot was actually doing during the match. So matches are uploaded to the Blue Alliance, and we can take advantage of this by actually downloading the video onto AdvantageScope. We can click the TBA icon on AdvantageScope, and the correct match will be fetched automatically. As the video download starts, it's important to here. So once the video is actually downloaded, it's synced automatically to the log within like plus or minus 1 frame, and there's no actual manual work required to sync it up manually. So now that we have the video, we can open another useful view, which is the joysticks view. And this can show the states of the actual joysticks during the match. Joystick data can be logged automatically by WPILib, and we can represent it in this view. So as the match plays on, we can see what the drivers were doing moment to moment, and this allows us to distinguish between what the driver was doing and how the software might have acted up. So now we'll focus on an actual case study of what happened during an actual match. So we can replay what happened during the video in 25% speed to see everything more clearly. As we start racing back to the hangar, here we go for the cable bump, and the driver lets go of the joystick. The top of the robot keeps on going because of inertia, while the bottom of the robot stops immediately. This causes the whole robot to tip over, and it tips. After a difficult moment like this on the field, it's important to be able to distinguish what happened by what the problem was with the driver versus what happened with the software. So here we were able to review what happened, what did the driver do during the match. And we were able to see in detail that the driver should not be letting go of the joystick when they're going for the cable bump. And so we told the driver about this, and they never made this mistake again. So this shows how logging can not only be useful for the programmer, but also for the whole drive team.
We can also merge the same data source across multiple matches. Let's merge the logs from playoffs at our first 2024 event. We'll first start off by selecting 5 log files. AdvantageScope will start loading these automatically. It's about 150 megabytes of data. As soon as it's loaded, AdvantageScope automatically merges and synchronizes these by looking at the enabled fields. During auto, you can see that we're relatively consistent. We have a few outliers. Maybe we hit another robot during the routine. Now, when we switch it to teleop, we can see how we drove throughout the match. You can see our cycles aren't too consistent. Our lines are kind of all over the place. Now let's move on to our second 2024 event. Same thing here. Let's start with autonomous. You can see we have more variety in our autos. We're going for different centerline nodes, and we're running different autonomous routines. It's nice to see that we're still fairly consistent on the pathing. And now when we switch to teleoperated here just in a second, you can see that our lines are much more cleaner. We can see the difference between what cycles we're feeding, what cycles we're scoring. This is really helpful for drivers when reviewing their behaviors during a match.
Another useful thing that we can do with AdvantageScope is visualize actual game pieces in 3D, and this has lots of potential applications. One might be visualizing actual auto routines and how the robot interacts with the game pieces. For example, it might intake it, it might shoot it, and we can actually model the trajectories that the game pieces take on the simulator. So we can run this play a bit. These are the past 3 years, including this event, and we can see how the cubes can be intaken by the robot, how we might shoot the notes into the speaker, etc. But it can be even simpler. Here we're just showing whether a game piece is actually in the robot based on the output from a sensor. And this can be done with an easy, just one line, just log whether the sensor detects a note inside the intake. And we can visualize it in AdvantageScope.
Okay, so now for something particularly special. Now, we're always working on new features for AdvantageScope, and each year we release a beta in the fall before a final version right before kickoff. And each year so far we've included some headlining new features. In 2023, that was when we added the 3D field, WPILog and network tables support, and a bunch of new visualizers. In 2024, we released cinematic mode, the heat map, field search, automatic video downloading, and some enhanced log merging features. Now, there are lots of things that we're working on for 2025, but we wanted to give a sneak peek into one that we've been experimenting with. And that feature is AdvantageScope Extended Reality. So this includes augmented reality, where objects are overlain on the real world, virtual reality, where only a virtual world is visible, and options for objects that are rendered at different scales, from full-scale rendering to miniature models. So what does this actually look like? Well, we have some early prototypes to share, but keep in mind that all of this is very much still subject to change. Okay, so one of the first things that we tried once we got this running was to simulate an auto routine. So here, the robot and the game pieces are being overlain on our real practice field. So we can walk around and see this happening in 3D, we found that this was really great for getting a sense of scale and figuring out potential failure points of the autos. And in fact, when this video was recorded, our competition robot looked like this. So you can see why it might be helpful to be able to run it in a virtual way. We found that even the mechanical team just enjoyed being able to walk around the robot and see it in action before it was actually completed. Another use case for this might be after the robot is finished, you could overlay data on top of the real robot to see vision targets, trajectories, set points, useful information that can help you with debugging what the robot is actually doing. But of course, AR can also work in miniature. So let's say you wanted to put a field on your tabletop, and you could stand around and watch the match with drivers from any angle. You could also make it fill up your room and walk around it. You could see how that might be particularly helpful for seeing the field at kickoff when you've never been there in person. And in full scale, you could even overlay the field elements and robots on a full-size practice field, even if you only have a carpet set up. And we also would like to add support for VR. So here's a simple demo of that. We want to enable experiences where you could, for example, watch an auto routine behind the driver station and see what it would actually look like running it during a match, even if you don't have a physical robot to do this with, or a practice field that you can run it on. Okay, so that's AdvantageScope Extended Reality. As I said before, all of this is still in very early development. So the release date, device support, etc., those are all to be determined. But we think that there's a lot of potential here, and probably use cases that we haven't thought of yet. So we wanted to share this early so that you might start to think about how this could be helpful for you and your team. And of course, there are lots of other improvements that we're planning for next year, including a bunch of quality of life enhancements that have been suggested by the community. Okay, so just to summarize what we talked about today, so we went through how to get started with logging, how and why to use AdvantageScope, why merging multiple data sources is valuable, and how AdvantageScope enables advanced visualization with game pieces and extended reality. So finally, here are some links to the tools that we've talked about. You can also contact us by emailing software@team6328.org. But thank you all for listening, and we have a few minutes if anyone has questions.